All right, so this is section 15.3, video 4. This will definitely be our last of the videos. So this one says just simply sketch the region of integration and change the order of integration. So we don't actually have to do this one because there's no function, it just tells us f of x, y. We just need to figure out what it looks like to change the order of integration to a dx, dy, or to a type 2. So right now, it's in a type 1. And if we were to sketch what this thing looks like, let's see, the x goes from 0 to 4, y goes from 0 to the square root of x. So y is going to go from 0 up to the square root of x, and x goes from 0 out to 4. So right now, that is your type 1 region. Again, this right here was the square root of x. So now if we want to change this, we want to change it into a type 2 region. Okay, it's the same exact functions, so they look the same. The only difference is now we want to go this way, left to right. So we want to go, instead of y being the square root of x, instead of y equaling the square root of x, we want to solve that for x, so we know that y is the square root of x. We square both sides, so x is going to be y squared. So this now becomes y squared in terms of x. So now x is going to vary from 0 to y squared. I'm sorry, y squared to 4. Because here's y squared, here's 4. It's got to go left to right. Y squared to 4. And y is going to go from 0 up to whatever that intersection point is. Well, if I plug 4 in for x, that's going to be y equals 2. So it looks like our domain for the type 2 region, again, x is going to go from y squared to 4, and the y values are going to vary from 0 up to 2, up to y equals 2. So now we can write our double integral. So the double integral is going to be 0 to 2, y squared to 4 of f of xy, and now it's going to be a type 2, so it's dx dy. And we've rewritten a type 1 as a type 2. Again, it's very important that you can do that just in case you need to change the bounds order of integration for some reason. All right, one more example to go. We want to evaluate the integral from 0 to 1, integral from inverse sine of y to pi halves of cosine of x plus 1 plus cosine squared of x dx dy by reversing the orders of integration. All right, so this one's going to take a little bit of work because we got to figure out what this thing looks like. So x goes from the inverse sine of y to pi halves. Well, the pi halves part is not difficult. That is a vertical line. The inverse sine of y. Inverse sine of y, maybe not something that you're going to be like used to seeing, but basically it looks like this. Now remember that inverse sine basically is bounded between well, it's bounded between negative pi halves and pi halves, but remember that sine itself can only go from -1 to 1. So this top bound right here, because inverse sine of pi halves is going to be 1, so that's 1 right there. So that's going to help us later on. So right now this is, let's see, that's a type 2 region because it's dx dy. We want it to be a type 1 region. Let's actually write out the bounds here that they've given us. So x is going to be between inverse, not negative, inverse cosine of y is less than or equal to x, which is less than or equal to pi halves. And right now, y goes from 0 to 1. So the one that I really need to focus on here is this piece right here. So how am I going to solve that piece for y to change the bounds? Well, to get the inverse sine of y out of there, I'm going to take the sine of both sides. So really, y is going to be less than or equal to the sine of x. So this piece right here is going to go, now that it's type 1, which will be that direction, y is going to vary from function to function. So y is going to go from 0 up to the inverse sine, up to the sine of x. So y now goes from 0 to the sine of x. And x is going to vary from number to number. So x is going to go from 0 to pi halves. So let's go ahead and set this thing up. We're going to have the integral from 0 to pi halves, integral 0 to sine of x of cosine of x square root of 1 plus cosine squared of x dy dx. So now we're taking the antiderivative first with respect to y. So let's go ahead and do that. So we're going to get y cosine of x square root of 1 plus cosine squared of x evaluated from 0 to the sine of x dx 0 to pi halves on the outside. So plugging in the sine of x, I'm going to get sine of x cosine of x square root of 1 plus cosine squared of x. Plugging in 0 fortunately gets rid of all the rest of it, so that's really nice. Integral from 0 to pi halves dx. So I'm definitely thinking we're going to have to do some substitutions here. It looks like because it'd be really nice if that was 1 minus cosine squared of x underneath the square root, because then that just would have been sine, but it's not going to be the case. So I think we're going to have to do u equals the whole inside of that square root, 1 plus cosine squared of x. I don't think just letting it be cosine of x would work, because you'd still have an extra cosine on the outside. So yeah, I don't think that's going to work. So du here, oh yeah, this will work, is going to be, let's see, the derivative of 1 plus cosine squared of x. Well, that's going to be 2 cosine of x times the derivative of cosine, which is negative sine of x, dx. So solving for dx, we get du over negative 2 sine of x cosine of x. That's good, because that will get rid of what we have on the outside there. All right, do we want to change the bounds? Yeah, let's change the bounds. So if I plug in 0 for x, it's going to be 1 plus cosine squared of 0. Cosine of 0 is 1, so squared is still 1, plus the extra 1 is 2. So we get a 2 down there. Plugging in pi halves, cosine of pi halves is 0, so that just means I'm going to go from 2 to 1. Let's see, I'm going to have sine of x cosine of x square root of u times the new dx, which is du over negative 2 sine of x cosine of x. So the cosine x, sine of x both cancel out. I do have a negative 1/2 I have to pull to the front. Negative 1/2 integral from 2 to 1 of u to the 1/2 du. I'm going to go ahead and switch the bounds of integration, literally flip them, because remember that if you have a negative out in the front, you can switch the bounds by making the whole thing negative, basically multiplying by an extra negative 1. So now it's going to become 1/2 the integral from 1 to 2 of u to the 1/2 du. That's just a property of integration. All right, so the antiderivative is going to give us, let's see, that's u to the 3/2, so we multiply by 2/3 and evaluate from 1 to 2. That's going to be 1/3 on the outside, 2 to the 3/2 minus 1 to the 3/2, which is 1, and I think that is plenty good enough for that problem. I don't feel like simplifying it any further. We are done.